Today we are going to be solving systems of equations by graphing. And before we start doing that, we want to make sure we know what a system of equations is. So a system of equations is a set of two equations that share a common solution. So what that means is when we graph them, the solution is the intersection of the two lines. It is where the two lines cross. Graphing linear equations is one method to solving a system of equations. So we are going to learn two other ways to solve a system of equations, but for today, graphing is how we are going to solve. Before we actually get into graphing, we are going to look at graphs that are already done for us, and we just need to identify the solution. So like I said before, the solution is where the two lines intersect. So looking at this first example, I want to identify where they cross or intersect at and draw a little circle there. And then I just need to identify that ordered pair. So remember, we start at the origin and I'm going to count over first and then up or down depending which direction. In this case, I'm going to go up. So I'm going to go over 1. So my x value is 1. And then I'm going to count up 2 to get to where the lines cross. 1, 2 is the solution for this graph. Looking at our second example, I'm going to find where they cross at. And again, I need to identify the solution. And the solution is where they cross. In this example, I'm actually not going to need to move left or right at all because my point is just straight down on the y-axis. When that happens, I'm not moving left or right. My x value is 0. And then I need to move down 1. And because I go down, my answer is going to be -1. So the solution for the second graph is 0, -1. All right, and there are a couple special cases when we're talking about graphing lines and having solutions. So up above, they have in these examples, there's one solution because the lines intersect at one point. Down here, we're going to have those special examples. So if the two lines that you have never intersect, that means the lines are parallel. And the answer would be no solution. If the two lines are the exact same, there are infinitely many solutions. And this means that the lines are overlapping and they go on forever and ever. So any point on the line is a solution. All right, so this first example, we have parallel lines that never touch, never cross, never intersect. That means they are parallel, and their answer would be no solution. We can use the abbreviation NS for no solution. And our second example, they are the exact same line, which means there are infinitely many solutions. And again, we can use the abbreviation IMS to represent that. Moving on, we are going to get into graphing systems of equations. And our first example, we have y equals 4x minus 3 and y equals 4x plus 1. So we're going to want to graph the first example. And this is in slope-intercept form. So I'm going to start at my y-intercept of -3. So go down to -3 and put a point. And then my slope is with the number that's with x. So in this case, it is 4. And when there's no number underneath, we add the 1. So 4 over 1. I'm going to go up 4 to the right 1. And I always tell my students to always go to the right for that bottom number. 1, 2, 3, 4 over 1. And then we can go ahead and graph the line, connect it. I'm going to connect it as best I can. Okay, and then we're going to graph the second one. I'm going to start at +1 this time on the y-axis for my y-intercept, and my slope again is 4/1, so I'm going to go up 4/1 and connect it. Again, I'm doing it as best I can on my computer. If you look at these, you notice that they never intersect, and when this happens, they're parallel. Our answer is no solution. Looking at our next example, we have y equals 1/2 x minus 4 and y equals -x plus 2. So we're going to go ahead and graph both of those on the same graph and see what we come up with. My first equation, the y-intercept is -4. So I'm going to go down to -4. My slope is 1/2. So up 1/2, do it a few times to have a more accurate line. And then we connect it. My second example, y equals -x plus 2. I'm going to start at 2. And then my slope is negative. There's a 1 there, so -1/1. That tells me to go down 1/1 from my y-intercept. And I'm going to keep going until I get to an intersection there. Connect it. And you can see that this does intersect where I just highlighted. Now we need to identify what that ordered pair is. So I'm going to count over. It looks like it is over 4, down 2. So my solution would be 4, -2. I want to do one more example where we have one of the equations in standard form, just because you graph that a little bit differently. So this example, our first equation is in slope-intercept form, so we can graph that just like we've done the last two. So I'm going to start at my y-intercept of 6, and my slope is -2/1. So I go down 2/1, down 2/1, do it a few times, connect it. The more points you have, the more accurate of a solution you're going to get. The second equation we have in standard form, and when we have standard form, we want to identify what is our x-intercept and our y-intercept. And to do that, what I always show my students is we want to cover up or plug in 0 for y. So when we plug in 0, anything times 0 is 0. So I'm left with 24 divided by 8 when I solve for x, and 24 divided by 8 is 3, so my x-intercept is 3. And then I would do the same thing to find the y-intercept. I would plug in 0 for x, so this would be 0, and I would be left with 4y equals 24. To solve for y, I would do 24 divided by 4, and that is 6. So my x-intercept is 3, my y-intercept is 6. I'm going to go ahead and graph those, 3 on the x, 6 on the y. And when I connect that, if you notice, it is the exact same line. And when this happens, our answer is infinitely many solutions. The last thing I want to talk about is determining if an ordered pair is a solution to a system of equations. So we can decide, given an ordered pair, if it is a solution to the system that we are given by plugging in the ordered pair for our x and our y terms in the equation. So I have the point -3, 1. That is my ordered pair. I'm going to plug in -3 for x and 1 for y to see if it equals whatever the equation is equal to. It has to work for both equations for it to be a solution to the system. If it only works for one equation, that is not a solution to the system. So we're going to verify that these are solutions or are not solutions by plugging those in. So I would have -3 for my x plus 1 for the y equals -2. And when I simplify -3 plus 1, that is -2. So that works. Then I need to double check that it also works for the second equation. I would plug in -3 for x plus 5, parenthesis, plug in that y value for 1, equals 2. When I simplify -3 plus 5 times 1, that equals 2. And that does in fact equal what this equation is set equal to. So when we get verification for both of them, we can say that yes, -3, 1 is a solution for that system of equations. Let's take a look at the second example. Again, plugging in our x and our y values into the equations down below. This one is a little bit more complex because we have coefficients. So we have 2 times 5 minus 3 times 2 equals 4. All right, so I'm going to simplify this. 2 times 5 is 10. 3 times 2 is 6. 10 minus 6 is 4. And if we bring that up, that is equal to 4. So that one works. Now we want to double check that it works for the second equation. I have 2, plug in 5, plus 8 times 2 for our y value equals 11. So if I multiply this, 2 times 5 is 10. 2 times 8 is 16. 10 plus 16 is 26. Over here we have equals 11. Unfortunately, this time 26 does not equal 11. So we know that the point 5, 2 is not a solution to that system of equations.